Hello, these are the 7th grade individual competition solutions for the middle school Math Honor Society competition. Let's just start with the first one. So I'm just going to copy this and paste it on my whiteboard. Okay, so this one isn't too bad. It's pretty straightforward. You just gotta think of the idea of parts of a whole, right? When it says Raj ate 1/3 of a cake, it's kind of like saying what's 1 minus 1/3 minus a sixth of the remaining cake does not mean minus 1/6. It means minus 1/6 of what's already remaining, right? You'll see that after a while this gets a bit computationally annoying. So a good way to think of it is just subtracting by 1 each time. So Raj ate a cake, right? Because we're anyways trying to find out how much cake is left over. So if Raj ate a cake, or 1/3 of a cake, that means 2/3 is left. Now Bianca ate a sixth of the remaining cake, so that means that 5/6 is left, so you just multiply by 2/3. And Aaron ate 2/5 of the leftovers, so that's just multiplying by 3/5. This is nice because a lot of fractions cancel, or a lot of the parts of the fraction cancel out, leaving you with 2/6, which is just 1/3. Okay. All right. So now next problem is how many ways can the 5 people be standing together? Let me just delete all of this and then okay, so how many different ways can the 5 people stand together if 2 people must be seated together? So this is a pretty nice problem because there's a nice way to think about this, right? So before we even add any restrictions, right, let's just ignore the restriction. What will happen? So if they can't even stand each other, we're just seeing how many different ways can these 5 people stand together. So let's just have them as A, B, C, D, E. That's a pretty common math team problem. That's just going to be 5 factorial, right? Because you have 5 choices for the first person, or then 4 choices because one's gone, and then so on and so forth, right? Now, we have a restriction. We have that these guys must be sitting next to each other, right? So 5 factorial isn't going to work. But think of it this way. If they have to be sitting next to each other, right? Say you have A, C, B, D, E. You can actually just group these together, right? Literally just group them together and have them as like, I don't know, G, something like that. G for group. Now you can just have A, C, G, and E, right? And it doesn't matter because if we find out how many different ways are there to order this, we guarantee that B and D are together. So that's 4 factorial different ways. But is that the final answer? No, because we got to realize that, hey, Bob and Doug, they're 2 separate people. They're not the same. They are distinct. So because of that, B and D, you can actually have the order where B comes first and then D, or the same, exact thing, like A, C, G, E, and D comes first and then we have E. So how would that look? That would literally just, in this case, it would just look like A, C, B, D, E, or A, C, D, B, E, right? 2 cases for the exact same main case. So that's 4 factorial times 2. That's just going to be 24 times 2. That's just 48. Okay, problem 3. So this one's pretty cool because it actually uses patterns that you wouldn't expect to find in a normal arithmetic or geometric series, right? In middle school, you mainly just have to worry about arithmetic and geometric series, where it's like, say, I don't know, you have 1/7, then you would have 2/7, 3/7, right? Where the numerator increases by +1. Here, that's not the same. In fact, the denominator decreases by 3. That's called a harmonic series. Now, to solve this problem, do you need to know what a harmonic series is? No. You just need to know what's pattern is going on. So you start with 1/19th, right? And, well, we know that it starts at 1/19th, and it has to continue, right? And so, logically speaking, this there has to be a greatest value. So what is that going to look like? We might not know. So I'll just show it how it looks when you're just writing them out. Because think of it this way, right? You're starting at 1/19th. When you go to 1/16th, does the fraction get bigger or does it get smaller? You might be tempted to say it gets bigger because the denominator gets bigger or smaller, right? But actually, we have a negative. That negative means a lot because technically, if we had a number line where I'm going to draw the number line like this, just so it's easier to visualize. This is negative 1/19, right? Because 1/16 is greater than 1/19, if you multiply both sides by -1, negative 1/16 is actually less than negative 1/19, right? That's just like inequalities. So that means that negative 1/16 is going to be like that. Now, that might be a bit confusing because you're like, well, my denominator, it's getting bigger, right? So because it's getting bigger, it's eventually going to approach, like, I don't know, 1 or 2. So that's what we're looking for, actually. That's exactly what the problem's trying to, like, get you on. So I'm just going to erase all this. I'm just going to continue just working, right? You have negative 1/19, negative 1/16, negative 1/13, negative 1/10, negative 1/7, negative 1/4. Now this is where stuff gets interesting, negative 1/1. Now we have negative 1. What comes after negative 1? We're just going to add 3 to the denominator like we've always been doing. So now we get 1/2, positive 1/2. Now we get 1/5, 1/8. And I'm not going to draw the rest of the numbers because you should realize that, hey, this is a pretty cool number, right? A half. A half is not negative, so it's automatically greater than all of these fractions, right? Additionally, 1/2 is also bigger than 1/5 and bigger than 1/8. So that shows pretty like something cool. Now, do we know, can we guarantee it's the greatest value of a term in the sequence? We pretty much can, because 1/8, right, after, like, the numbers just keep getting bigger. They're eventually going to approach infinity. You don't have to think of it like that, but just like you have to realize that this number is going to get really, really big. So I'll literally just say big, right? It's going to be really big. So because of that, it's always going to be less than 1/2. So 1/2 is just the answer. Okay. So there are, for this problem, there is a general formula for this. However, I'm not going to prove that formula. Instead, I'm going to kind of show a case of the formula. And if you want to try deriving a proof on your own for the formula, that's going to be awesome. If you don't want to do that, there's a video that Mr. Robo is going to send to your parents. That's just me just talking about a bunch of different math concepts that you're going to encounter in like high school math and even middle school math competitions. So I'm just going to show you this one problem, and I'm not going to, like, if you can generalize this idea to a formula, that's really cool. So yeah, so a 10-sided polygon, I don't really know off the top of my head what that looks like, so I'm just going to draw like 10 sides, right? What I'm drawing right now would be a 9-sided one, right? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm just gonna, doesn't have to be like perfect, right? But it just gets the job done. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I need one more side. So I'm just gonna take this and split it off into like 2. So yeah, this is a vertice, this is a vertice, this is a vertice, right? So the big thing is, right, if we want to find a diagonal, what's the definition of a diagonal? Well, it gives you it in the first part of the problem. It's just a line between two non-adjacent corners. So what does that mean? Let's just take a point, right? Let's just take this point, pretty like random point, I guess. So can I choose adjacent things? No, I'm going to cross out the things that I can't choose. So to make a diagonal, I can't choose this one, right? I can't choose this one because those two are adjacent. Can I choose the same point? No, I can't. So therefore, I cannot choose 3 of the points. So I have 10 choices for that first point, right? I have 10 different vertices to choose from. Now I'm like, okay, after choosing one vertice, I just eliminate 3 of my choices. I can't choose the ones that are adjacent, nor can I choose the one that it is. So therefore, I have 10 minus 3 solutions, or yeah, choices you can make. So that's just 10 times 7. Now, is the answer 70? No, it's not, because we made one like assumption, right? We're assuming that 10 times 7 shows that each diagonal is completely different from another. That's not true. Because say I choose the point that I'm choosing right now, and then I go to this point, right? Like I'm just going to draw like an arrow, right? Just to like show you what I mean, right? So that's an arrow. But now let's say I'm just choosing a different point, and I happen to choose that point again, and now I'm going back to this original point. Technically, my 10 times 7 would show that those are 2 different lines. But there are no arrows in diagonals. They're just straight lines. So I kind of butchered the drawing. But yeah, there's just one straight line. So that's why you have to divide by 2 because 2 is the amount of endpoints you have, so just 10 times 7 over 2, that's just 35. Okay. Alright, so problem 5. If 3 chickens lay 3 eggs in 3 days, this is a, you might have heard of the formula D equals RT. That's a really famous formula in like everywhere, like physics, math. You probably even heard of it yourself. So it's basically saying that the distance you travel is equal to the rate times your time. Now, why am I saying this? Because it's a pretty easy formula to understand, right? It's just rate. Like say I'm going 5 meters per second and then I travel a second. How many meters am I traveling? I'm just traveling 5. The reason it's good is because D equals RT doesn't just apply to distance. It actually applies to any amount of task equal to the rate at which you do tasks times the time which you do the tasks for. So what does this mean? We can apply this to chickens and eggs. We can say that, so generalizing the formula, we have the time in days, so I'll just say days, times the chickens, or I'll just say chicken rate, is equal to eggs, right? And why do I say chicken rate? Because here it says 3 chickens, so I'm just going to say the rate of 1 chicken laying an egg is C, so here it would be 3C, right? Now, what's the first equation? That just says that in 3 days, 3 chickens, so 3C is your rate, is equal to 3 eggs. And then what you have to see is how many eggs will 1 chicken lay in 2 days. So that's just C times 12 is equal to E. I don't know how many eggs, so I'm just going to say that as E. So this is a system of equations. What you can do first is C is by itself here, right? If you solve this equation, you just get C is equal to 1/3. And plugging that into here, you have 1/3 times 12 is equal to 4 eggs. Okay. I'm just going to close this tab. All right. So, problem 6. A square is inscribing a circle. I don't know why it says that inscribe is like not grammatically correct. Usually all the math competitions just say inscribes. It's like, it is what it is, right? Grammar is not the focus of this problem. But anyway, so what I'm actually going to do, I'm going to enlarge this diagram really, actually, you know what, better yet, I'll just have this problem small and then enlarge the actual picture so you guys can see like exactly what this problem is saying. So, okay, perfect. So we have our diagram here, and the square describes a circle. So, how many different ways, or can I like represent the radius, right? You could say something like this, right? That's a pretty bad picture, so I'm just going to use like blue. So you can say like this is the radius, right? And the reason this is annoying is because we have this like side length, which we don't know, right? That like area past the square, but before the circle is something we just don't know. So it's really annoying to work with. So what you actually can do is think of it like this. Instead of drawing the radius like that, why don't I start from a point where they intersect and go to the center? So that's one radius. What is that value? That's just 5. So I'm just going to write 5. And so that's how you can represent like the circle inscribed in the circle, or the square inscribed in the circle. And let me just backtrack a bit. It's asking what is the shaded area. How do I even find the shaded area? Well, that's just the area of the circle minus the area of the square. And what is the formula of the area of a circle? That's just pi r squared. What is the area of a square? That's just s squared. Notice that r and s are different variables. So we have that, and radius of the circle is 5. So we can just plug that in, just have 25 pi. And a square, we don't know the side length. So that's what we have the diagram for. So we don't know that, we know that this is 5. I'm just going to draw this as like a 5 just so it doesn't get confused as an s. And now we are in a position where we don't know what to do to find the side length. And something cool you can do is identify that, hey, this is just a right triangle in the skies. I might actually just have it as blue. So it's just a right triangle in the skies, right? And we don't know the side lengths of the right triangle, but we do know that it's a right triangle. And if you have done a lot of math team before, you might realize that, hey, this is a 45, 45, 90 triangle, right? So there's like ratios where you can use, where you can just figure out what the side length is immediately and work from there. However, I'm just going to go under the assumption that you don't know this ratio or this trick because technically they cover it in 8th grade in geometry. So it's not a big deal. It's really easy to derive. So first of all, it's a right triangle, right? Two things I'm going to say. First thing is that I'm going to have this length as s. Second thing, I'm going to have that other side length as s. Why? Because it's a right triangle, but it's also an isosceles triangle. And the reason it's isosceles is because this is 45 degrees, and this is also 45 degrees. If you don't know why it is, it's just because, think of it this way, right? You have like the whole square, and you're just literally splitting it in half by 90. So 90 divided by 2 is 45. So once you get that, it's pretty easy, right? Just using Pythagorean theorem, you have s squared plus s squared is equal to 25. You're solving for s. So just 2s squared is equal to 25. 25 over 2 is equal to s squared. S is just equal to 5 over root 2. I'm just going to leave it like 5 over root 2 for now. But one more thing before we finish, right? We found s, but s isn't the side length of the square. It's the side length of the right triangle. Notice how two s's make up one side of the square. So that's pretty important to say because now we know that the side length that we need to square is just going to be 2 times 5 over root 2. So 2 times 5 over root 2 squared. So we just have 25 pi minus, I'm just going to use the trick that ab squared is equal to a squared b squared. So 2 squared times 5 over root 2 squared. Another trick I'm going to use is that if I have a over b squared, that's just equal to a squared over b squared. The reason that's true is just fractions, right? This just turns into a over b times a over b. So yeah. Okay, so 25 pi minus 4 times 25 over 2. Okay. So what is that? The 4 times 25 over 2 just cancels out one of the 2, so you're just left with minus 50, and then you just have a 25 pi. So that's your final answer. You might be like, oh, is that the right way to write it? Technically, yes, because we never said like if it's an integer or like if there's something to do with the area. We just said give the area, and I'm pretty sure it said exact area too. So yeah, what is the shaded area? So exact area, just leave it in this form. It will be fine. If you also, yeah, 25 pi minus 50, that's perfect. So yeah. Okay. The degree measure of one of the two complementary angles is 3 degrees less than 2 times the other. Okay. So this is using a bit of geometry. And this is a 7th grade competition, so this is kind of more of like a for those who are in math team, but it's okay. I'll just show you how to do it. So complementary angles just mean if you have two angles A and B, right? They add up to 90 degrees. And you can kind of build something off of that, saying the complement of a angle A is just going to be 90 minus A. So that's just some context. So it says degree of measure of one of two complementary angles. So we just have the first one, A and B. So A is equal to 3 degrees less than 2 times the other, right? And that's just all there is to it, right? It's just a system of equation. And if you know what a complementary angle is, that's perfect. You just got most of the problem done. If you don't know, it's okay. It's just one problem, but complementary, just try to remember that it adds up to 90. So yeah, they add up to 90, and then one of the two is 3 less than 2 times the other. So what is the greater angle? Well, we'll have to solve for A and B and see which one it is. But yeah, so substituting A into this just gives you 2B minus 3 plus B is equal to 90. So 93 is equal to 3B. And then B is just equal to 31. So if B is equal to 31, plugging that in will just give us 59 for A, because 90 minus 31 is equal to A. And which one is the greater angle? It's 59. Okay. So this one looks pretty scary, especially if you've not dealt with radicals before. So yeah, but this is just, so I'll just show you how to just simplify radicals. It's kind of straightforward if you already know the process, but if not, it's okay. So 98, right? We got to look for perfect squares that fit into each of one of them. So 98, I'm going to actually do 32 first because I'll show you something that you can do. So 32, I'm going to simplify this all the way down, right? 32, that's just equal to 16 times 2, right? Square root of 16 times 2. Which is also equal to 16, or root 16 times root 2, which is just 4 root 2, right? So this is simplified to that. Now, the reason I turned the 32 first was because, first of all, it's easier. It's a small number. Second of all, it's a times a root 2. That means that if I want to combine these two and make it a simple radical with only one radical instead of two radicals, I need to turn it into something with a root 2. That's just kind of like foresight and just planning. Like, you want to plan ahead. Because 98, I could have been like, oh, I don't know if it like has like a simplifies down into a root 2. Now I know. So I know that I need something. So root, like, so you need something that's 98 can be split up into something that's square root of something times square root of 2. Kind of saying that bad, but what I'm trying to say is that I have two radicals that when combined, they give me 98. However, I know one of them is already square root 2. So now we just need to find out what the other radical is, which means that it's just, if we had like x for that, it's just 2x is equal to 98. So 49 is just 98 divided by 2. This is cool because root 49 is just 7. So we just have 7 root 2. So it's just asking what is 7 root 2 minus 4 root 2. Well, if this seems complicated, replace it with like x is equal to root 2. If I have 7 of something minus 4 of that same something, that's just equal to 3 of that something, which in this case is just 3 square root 2. Okay, so page 2. When 2 is subtracted from half of a number, so I'm just going to write, this is just another one of those where you just need to take the equation and just turn it into a, or no, take the words and form it into an equation. So I'm saying you have a number, right? I'm just going to n. So n over 2 is half that number, because if you also want to think about it, like look for keywords, right? Half means division or multiplication. Subtracted and addition, they just mean subtraction or addition, right? So always think of PEMDAS, right? I know you probably didn't expect PEMDAS to appear, because I know I haven't used that word in a long time, especially in high school math. But the thing with PEMDAS is that it helps you with these types of questions, because you're like, sure, it's like 2 is subtracted, but I want to be thinking of the multiplication. I want to be reading ahead. So now I have 2 is subtracted. So n over 2 is, you're going to subtract 2. It is equal, that just means an equal sign, is equal to 3 added to that same number. So here's our equation. Now we just have to solve. So I'm just going to multiply everything by 2 because there's a 2 in this denominator. So we have n minus 4 is equal to 6 plus 2n. Subtracting the n over here to this side, we just have n. And then it's negative 4 minus that 6. So negative 10 is just equal to n. Okay, problem 10. John and Nishal. Okay, perfect. Okay, John and Nishal are 30 miles apart. John is biking towards Nishal at 12 miles per hour, and Nishal is jogging towards John at 6 miles per hour. Now, you might be like, okay, in problem, I don't know, which problem was it? 5, we talked about the idea of d equals RT. So the thing is, d equals RT is one way you can use to solve this problem. How would you do it? Just be like, okay, well, like I'll just have John as the distance, or J as a variable for distance traveled by John, and then n for Nishal. You know that J plus n is equal to 30, and then you can solve for your individual rates. Because if you want to think about it, like think of it as like a graph, right? When you start the time, when time is equal to 0, they're at their like 30 miles apart, right? So that's cool. But when they meet, has one time progressed faster than the other? That doesn't make sense, right? Like how can it like just think like that just doesn't make sense at all? Because you can't have it where one person meets the other person at a quicker time. Like it literally just becomes paradoxical at that point, right? So you can just use d equals RT where t is the like same thing. So that's just having j is equal to his rate, which is 12t, and n is equal to his rate of 6t. Why is that cool? Because even though we have 3 variables, we also have 3 equations. So we can substitute that for that, and then that for that. So we have 12t plus 6t is equal to 30. So that's cool because we have 18t is equal to 30, right? Solving for time, we get this. We get time is equal to 30 over 18. and we can take time and turn it back into John's original equation. So there's a lot of variables and a lot of things to keep track of. This is definitely one way you can do it. This is the way I would do it if the numbers hadn't worked out so perfectly. The reason I'm saying that is because, like, in a lot of high school math problems, you'll have it where it's like 9.3 and then like 7.2. There's nothing really cool about those two numbers together. So you would probably want to do the solution. Now, let me show you something cool, right? I'll leave the rest of the solution for just you guys to do because it's pretty straightforward from there. So yeah, another way of doing, I'm just going to erase all this. What you can do is, first of all, I said like the numbers have to work out perfectly, right? Notice how 12 is twice of 2. So think of it like we call this in physics, we call this a I actually forgot the name of it. I know it's not position time graph because that's just like, yeah, I don't know the word for it. I think it's like it's with arrows, but basically it doesn't matter what it's called. So you have two graphs. You have John. So no, Nishal is going at his 6 mph. John is going at his 12 mph, right? Now, and let's just have time equals 0, right? That's just here. They're both at time equals 0, right? They're both at the position 0. Now, what happens if the time equals 1? At time equals 1, John, the 1 is just arbitrary, right? I'm just going to say 1 hour. Like, technically, it's not 1 hour because it's like they'll meet faster. But at time equals 1, John goes at 12 miles, right? But Nishal only goes half that. He goes at 6 miles. So the reason this is relevant is because for every time Nishal goes a amount of distance, John's going to go twice that. So you know that the sum of their distances is 30. So D1 plus, or I'll just have that as variables, right? John plus Nishal is equal to 30. But like I said, for every time John goes 1 mile, Nishal goes 2 miles. So I'll just say 2n. And this is cool because we can also plug this into the same equation, right? So we have solving for, like, it's easier to substitute for j because we already have it. So 2n plus n is equal to 30. So n is equal to 10. That's Nishal's, but we're looking for John's original distance. So that's just 30 minus 10, giving you 20 as your answer. So 2 ways to do the same problem. Both really interesting ways of doing it. Whatever you like the most. Honestly, I like the idea of having that, it's just in a 1-to-2 ratio. So using the fact that the distances also have to be in the 1-to-2 ratio, that's a really quick way to do it. But sometimes your numbers just aren't going to work out perfectly. Even if it doesn't work out perfectly, you can still, it doesn't have to be like a 2-to-1 ratio. It'll still work out. It'll just be a bit more annoying to do computationally. But like I said, you don't want to try to generalize solutions to problems, right? You always want to see the context of the problem and how it affects the how you solve the problem. So problem 11. It's a nice geometry one. So EF is half the length of AD. So what is AD? AD is 8. EF is half of that. So we have 4. Now what is DEF? Well, this problem, I'm going to zoom in a bit more. Actually, it's fine. So yeah, you have 4. And you might be like, wow, well, I might have to solve for the big triangle. You might think that, solving for the big triangle and then subtracting the little triangle is maybe the way to go. But if you remember, the area for a triangle is 1/2 times base times your height, right? So in a normal triangle that looks something like this is your h, this is your b, right? B times h. The proof for that is because you can make a bigger square, and this extra stuff that we don't want is exactly half of the thing. Or in other words, the square that we make, or no, not the square, the rectangle that we make is twice of the triangle. Now, in other cases where the triangle is like this, right? You might think that it might not be able to be used, but the same thing still applies, right? You can still use the fact that you can make a rectangle, and this rectangle will be 2 times the other one. So, in other words, what I'm just saying is that we can still use 1/2 base times height, and that is just going to be, well, our height is over here, so you have 5 times 4 times 1/2. That's 20 divided by 2. That's just 10. Okay, problem 12. So, I'm just going to screenshot this real quick. Okay, Farshita has a total of 100 balls in 3 boxes. And so I'm just going to have, like, okay, so I have 2 ideas, right? I can make a picture, which that'll definitely help, right? That's one way to go about it. I'll just label these boxes A, B, and C. That's just a good visualizer. Now, we know that the total is 100 balls, right? So that's A plus B plus C is equal to 100 balls. Now we got to think of like boxes, right? So we know that A has 3 less balls than the second box. So that's just B minus 3. The third box, C, has 13 more balls than the second box. And so now what? We need to find the second and third boxes, their sums. We need to find B plus C. So how do we go from here? First thing I notice, probably the biggest thing in this problem, is that we already have 2 equations in terms of V. So this is cool because we can plug it into this equation and have the whole thing kind of just like unravel, because we can solve for a B, and then solving for a B can get a C. So like what I'm kind of doing here is like later just like planning out what I want to do, right? If you, instead of just jumping in and doing the math, I'm just taking 10 seconds to see what do I have, what can I get, how is that like, how is what I'm gonna get gonna affect my future, right? So kind of just having foresight, just planning it out, like determine like in programming you would call this pseudocode. Same thing here, right? I'm just looking at what I want to do. So plugging in A and C, I have B minus 3 plus B plus B plus 13 is equal to 100. And this is just 3B plus 10 is equal to 100. And from there, it's pretty straightforward to solve for B. You just subtract 10 from both sides. So 3B is equal to 90. And B is equal to 30. This is cool because you can plug in, you know that C, the other box, we want to find the third box, is equal to B plus 13. Plugging in B, we know that C is equal to 43. Now, we know that we need to find B plus C. That's just equal to 43 plus 30, which is equal to 73. Sorry. So, yeah, 73 is your answer. Another thing I was going to also mention, sorry. Another thing I was going to mention is that the idea here, like every, I think we've only had one problem in this test that you've only had 2 equations in system of equations. And you might be like, okay, well, like why is that relevant? I'm saying this because you don't learn how to do like actual 3 by 3, like 3 equations in 3 variables, like for example, like x plus y plus z, and like this with coefficients. You wouldn't learn how to do that until like algebra 2. However, what math counts likes to do is try to scare you by giving you a lot of like equations, and they're not going to be in a really bad format, or if they are, there's going to be some trick to going about them. And in this case, it's literally just thinking like, yeah, sure, you have 3 different equations, but 2 are already so easy to substitute into this. It's pretty much just having 1 equation. So just keep that in mind. Don't be scared. Just try to like persist. And like my favorite way, write out all your information. Then just take 10 seconds, just like stop and relax. Be like, what do I like have, and what can I go from there? So yeah. All right. 13 is an expected value problem. Expected value problems are fun because they're like one of those types of problems where you don't really cover them a lot in class, which is kind of annoying. But the nice thing about them is that expected value is probably the highest application of probability, especially in economics, right? Because who doesn't like want to know how much money they're going to make? So yeah, like lottery tickets, like that's a whole expected value thing. So yeah. Okay, so what is the expected value of the sum of the roll of a regular die with equal chances? So that's just a normal die. But now we also have an unfair die that is equally likely to roll the numbers 1 and 5, but rolls the number 6 thrice as much. So I'm going to handle this separately, right? The regular die, so the formula for expected value, I'm just going to say EX, is equal to your probability, so P, times your V, which is value. And you just sum these, right? So I'll just say like, just a sum. So it's just like all your P times V's and then sum. So the best way like to think about it is like a table, right? So for the regular die, I'm just gonna have P on one and then V on the other, right? Nice chart. So 1, 2, 3, 4, 5, 6. Those are your 6 different values for the die. All of them just have a normal calm value of 1/6, right? Because it's equal probability. All right. And then what does this mean? This means that like the expected value of this is that it's like 1/6 plus 2/6 plus 3/6, etc. So I'm going to calculate that in a bit. Now what I'm going to do is talk about the other one. The other one is the unfair dice. So what does that mean? Okay, so you're rolling the number 6 thrice as much. So what you have is also like a chart with P and then V. You have the same values. I'm just gonna move down a bit. And P, how you would just go about it is just calculating it, right? You have X as all of your probabilities. So I'm just gonna write X to the side. Or I'll just write it up here. So you have your sum of the probabilities needs to equal 1. That's just like a general probability thing. So if you notice, all of these add up to like 1, right? So you have X plus X plus X plus X for your 5 numbers, but then 3X. That's your probability for getting 6. That's just equal to 1. So how many X's do I have? 1, 2, 3, 4, 5. 5 plus 6. So you just have 8. X is equal to 1. So X is equal to 1 over 8. Now we have 1 over 8. 1 over 8. 1 over 8. And then 6 is just 3 over 8. So if you don't understand what I got, I just use the fact that the sum of all your probabilities add up to 1. Like really common probability thing. And then just work from there, right? Because you know that all of them are the same, so you just use variables. That's just my trick. That like it's pretty much just most people's general intuition. Now, what is the relevance of this? The relevance of this is that I need to now find out what is my expected value. So what the expected value is just your probability times your value. Just added all of those up. So I'm actually going to do myself a huge favor and split it off into the different dice, right? So I'll have fair dice and unfair dice. Because you can handle them separately, and why that is just literally like they're separate dice, right? So they contribute separately to the grand total. So if you find the expected value for one of the dice and you add it to the other dice, you'll have your total expected value. So what is the one for the fair dice? That's just one, like, so I'm just going to do, like, if you multiply all these probabilities, it's 1/6 plus 2/6 plus 3/6, etc., right? So I'm just going to do myself a favor and do 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6, right? What is that? You can use a summation formula. These numbers are small enough where you can just add them in your head. So that's just 21 over 6, which is just 3. Is it a coincidence that that's just half your total value? Wait, no, it's not even 3. It's 3.5. Yeah, that's what I was going to say. So it isn't a coincidence. But yeah, 3.5 is your expected value. Sorry about that. Because I was going to be like, wait, that doesn't make sense. But yeah, so other way of thinking of it, like this is just, since the probabilities are all equal, it's just the average of 1 and 6. So yeah, 3.5 is your expected value for your fair dice. Now for your unfair dice, I'm going to handle these 5 numbers separately. That's just same thing we did for this one, where it's just 1 plus 2 plus 3 plus 4 plus 5 over 8. And then you're also adding the, let me just move a bit to the side. Okay, plus that 18 over 8. Right? What is that? That's 15 over 8 plus 18 over 8, which is equal to 33 over 8. And now I'm like, okay, I have 3.5 and 33.8. Both of those are kind of like what do I do? Honestly, I just convert it to fractions, because when it comes to doing it by hand, I always trust my fraction math over my decimal math. So this is just 7 over 2. Converting it to 8 is just multiplying the top and bottom by 4. So that's just equal to 28 over 8 plus 33 over 8. That's just equal to 61 over 8. And that's just your final answer. So to recap, what do? We just found out that, hey, expected value, that's just your probability times your value. If you Google it, that's the formula you're going to get. And yeah, so using that formula, it's kind of like more of like a math counts thing. I know math counts loves asking about expected value. So yeah, you have that, and then just find out each dice separately because it's easier. Because another way of thinking it, I'm just going to go off on a little tangent here. This is like a nice like exercise, right? If I was to say, what are all the different, like, what are the frequencies of, if I have like 2 dice, right? I'll just, my poorly done dice, right? If I have 2 dice, and what are the different like frequencies of like values? You might be like, oh yeah, like the probability that you get a 1 is the same that your probability you get a 7. This is actually not true because like what I'm saying is that if you have 2 dice and you're rolling them, you're going to get 7 more frequently than you're going to get a 1 or a 12. And if you think about when like you're playing Monopoly, right? I used to play Monopoly a lot with my family, and like we would always like try to get like the perfect number to get the boardwalk or whatever it was, right? So you'll notice that it's easier to get a 7 because there's so many other ways to add up to a 7, right? You could get a 1 or 6, a 2 or 5, a 3 or 4, and then like opposites of all of these. But to get like a 12, you need a double 6, which is very low probability of happening. Realize you also can't get a 1. I just realized that right now. But why am I mentioning this? It's because if you did it the other way, if you took the dice together, like you took the fair dice and the unfair dice together, you would have had to find out every other possible value. You'd be like, okay, what's the chance that you get a 1, right? That's what's the case you get a 1, or sorry, 2. What's the case that you get a 2? That's a 1/6 times a 1/8. What's the case that you get like a 7? Well, how many different ways are there to get a like 2, right? There's so many other math. Just do yourself a favor and split up the expected values separately. So yeah, that's pretty much all I have to say about this problem. So yeah, it's a pretty cool problem. What is cooler, on the other hand, is 14. 14 is a very commonly seen problem, right? Like it is one of the like oldest tricks in the math team book, in my opinion. The reason this is because it looks complicated. It looks like, oh man, like I have like so many things to add. But there's a really nice trick, and it's just like you'll see. If you know how to do these problems already, that's awesome. You've probably seen like a YouTube video or like something like that. I've seen a lot of like TikToks about this. If you don't know how to do it, you're gonna like prepare to have your mind blown, right? It's gonna be like a really cool way to do it. So you have this. Let me show you something. This whole thing is like something, right? But notice how it repeats. So if you really think about it, it's infinite, right? So at some point, like the infinites are gonna make it where that this smaller thing is the exact same thing as the bigger thing. Does that make sense? Like basically what I'm saying is that when you have that smaller radical, since you're going off to infinity, there are so many terms that the exclusion of these 2 terms does not matter at all. So it makes it really cool because if I said the whole thing was equal to like, what's it called? The whole thing is equal to 4. So in other words, I'm just saying that 4 is equal to the square root of 2x plus the square root of 4x times, and now I'm repeating myself, right? I have that bigger radical with the whole thing. So that's just me writing 4 again, because what I'm just saying is that it's the exact same thing. So I'm just like kind of setting it as a variable. Like if I have 4 and you're like, oh, well, what is 4? 4 is just this big radical. So I'm just plugging it back into that thing. So basically what I'm trying to say is that it's infinite, so you can just substitute within itself. And that's pretty much the entire problem, right? After you do this, the problem becomes pretty trivial. So I'll just show it the algebra real quick to solve it. So you have 4 is equal to root 2x plus root 16x. And how do you go about that? Well, you can just square both sides because you're solving for x. So you have 16 is equal to 2x plus square root of 16x. And now what you can do is be like, well, wait a minute. What you can do is that identify that you have square root of 16 can also be broken up into square root of 16 times square root of x plus 2x. So you don't even have to square, like, again, like you could move the 2x over and then worry about that. But we just have 16 is equal to 2x plus 4 square root x. And now, yeah, that's just an easier way to substitute it. You have 2 different ways of going about this. I'm just going to show you, like, the obvious way might be to, like, move the 2x over and then square for that. What you can also do is I'm just going to say, like, I'm going to make a, like, cool substitution here. I'm going to say, like, take the variable u, right? Let it equal to square root x. So u squared is just going to equal to x, right? Because it's square root of x squared. So this is just equal to 16 is equal to 2u squared plus 4u, right? Now it's a quadratic, so dividing everything. Now what I'm literally doing is just making a substitution so it's easier on myself. I'll show you what that means in 1 second, because now you have u squared plus 2u minus 8. And this is just a quadratic that is factorable, so yeah. Now I have 2 solutions, and this is the extremely important part. Because remember how I said that u was equal to square root of x? Because u is equal to square root of x, that means that now I have to re-substitute that back in. So root x, or actually I'm just going to go one step further and say that the roots of this quadratic are u is equal to -4 and u is equal to 2. Now I can take this information and say that x is equal to -4 and x is equal to 2. Or square root of x is equal to 2, right? And now what? Well, 2 things. First of all, this is just like, no, this can't happen, right? You can't have a, like, you can't take the square root of a number and get a negative number. That's just going to give you imaginary solutions. The second thing is, this is the, like, second part of the trick with these problems, is you got to identify your bounds, right? I'll show this with an easier example. If you have something like 3 is equal to square root of, like, x, or no, better yet, sorry, x is equal to square root of 3 times square root of 3 times, like, where it's like inside each other. Like, it looks bad, but can x be negative? Like, no, I'm taking a positive number and then multiplying it by a positive number. So x is going to be greater than 0. So you're going to get an extraneous solution, because an extraneous solution is just another way of saying solution that is just, like, pretty much garbage. So you're going to get a solution that's less than 0, and that's just not going to be, like, it just doesn't make sense in the context of the problem at all. So the reason you get an extraneous solution, it's kind of cool. You'll cover it more in, like, later on math, but it's basically because you're squaring it. So yeah, it's a whole fancy thing. So I'll probably mention it in like the video, like the video that just covers, like, the basic tips. But yeah, so this one, just know. So we're just back to root of x is equal to 2. So squaring both sides gives you the final answer of square root or x is equal to 4. Okay. So before I go on, I'm just going to recap what I did. 4 is equal to all of this, right? So I'm just making a substitution, and then I'm just solving for x. But because I have radicals, I'm just going to do a little trick where I, like, substitute the square root of x for a different radical, or a different variable. And that just makes the algebra easier, because now I can factor it. And then, yeah, that's, like, a trick I like to use a lot, and, like, a lot of people use a lot. It's actually, sometimes the problem writers will literally make questions where you can't solve it without a substitution. Like, if you don't make a substitution like this, like, the problem just becomes so much harder. So yeah. Okay, last problem. This one's just another nice probability one, and this one you just have to kind of, oh, not again. Okay, I'm gonna pause it real quick while I fix this. Okay, it should be fixed now. Yeah, I was able to paste it just fine. Alright, so, what is the probability that drawing the king of spades from a deck of cards? So what you got to do here is just essentially be like, okay, drawing the king of spades from, so what is the definition of probability? This is probably, like, a really, like, basic question I'm asking, but it's kind of gets the whole thing kickstarted, right? Probability, so I'm just going to say P, is, like, this essentially is the fraction of your desired, so not a number of desired outcomes over your number of total outcomes. Right? That's, like, pretty much just the general definition of probability. And the reason I'm saying it is because it actually has a lot of important context. That is, your number of desired outcomes, the reason it's important is because we have a desired outcome. We want to pull a king out. Now, how do you pull a king out? Well, I'm going to ask a different question. How many different ways are there to pull out a king, because you know that at least one of them is a king, right? So I want to pull out, like the idea is to pull out a king of spades that I want. So if I have two cards, I'll just say like C1 and C2. If one of them has to be a king of spades, the other one, there's 51 other cards to choose from that aren't the king of spades. And so therefore, the number of like ways to choose two cards that one of them is guaranteed to be a king of spades, that's just equal to 51, right? And you kind of think it's kind of like one of those things where you have to figure out why that's true, like in your head, like you have to figure out yourself to like really have it click. But yeah, other thing, you might be like, oh, well, why didn't you multiply by 2 for the order of the cards? These are just pulling out, like I'm making the whole assumption that this just order doesn't matter. Because if you do have that order doesn't matter, or order does matter, you have to solve it a different way, and it's a lot more complicated. This way is kind of more elegant. So yeah, so I have 51 desired outcomes, right? I have one card where it's a king, and 51 other cards to choose from that aren't a king, right? Because there's 52 decks in a card. Or, no, sorry, there's 52 cards in a deck. Okay, now, what are the total outcomes? This is where I'm going to kind of bank on the choosing formula. And if you don't know what the choosing formula is, I kind of explained in the Mr. Robo video. But what it is basically saying out of a group. So out of a group of size n, so group size n, I'm choosing R values, right? This is just called n choose R, and it is one of like the biggest parts of counting in math team. And it's important because what we're doing here, we're trying to find out, we're trying to find out the number of total outcomes, which, what is the number of total outcomes? Is it the amount of ways to choose two cards from a deck? No, because we have an initial criteria. What it really is it's given that at least one of the cards you pulled was a king. So how many different ways are there to do that? Well, I'm going to use complementary probably for this by saying that, hey, I have 52 cards and I'm choosing 2 of them, right? That's the total number of ways to just choose 2 cards from a deck of cards, right? 52 choose 2. I'll show you the formula for this in 1 second. Or I'll just show you this now. It's just so NCR is just equal to n factorial over n minus r factorial times r factorial, right? Big part of probability. And yeah, that's just a basic formula. There's a nice proof for this formula. Like I said, I'll probably explain it in the other video. But 52 choose 2. That is your total number of cards. However, that's not your given probability space. The number of total outcomes is your probability space where it's given that one of the cards is a king. So because of that, it's actually going to be 52 choose 2 minus the amount of cards that we don't want, right? And there's 4 cards where it just doesn't apply, right? So it would be so there's 4 cards that like are kings in the deck of cards. So the bad cases where both cards are not guaranteed a king, you can just like think of it like just removing the king from the deck entirely. So now you just have 48 cards, which none of them are guaranteed to be king because you took out the 4 kings. So you have 48 cards and you're choosing 2, right? This is the bad cases. That's why we're subtracting it from the total cases, if that makes sense. Because the good cases are at least 1 king, right? That was given in the problem. So if this is your number of total outcomes, I'm going to go down and say that the answer to the problem is 51 over 52 choose 2 minus 48 choose 2. And well, now the only thing left is to evaluate the fraction. Okay, unfortunately my computer like ran out of space or something, so it stopped the recording. Fortunately, all of the recording I did for most of the problem was done. Only thing that wasn't done was just getting this fraction simplified. I thought that I should probably finish the problem because this is also like simplifying this might not be the easiest thing to come across. So I'm just gonna do it, right? So 52 choose 2, right? What is that? Using the formula, that's just 52 factorial over 50 factorial times 2 factorial, which is just 52 times 51 over 2, right? That's another trick. Like if you have something that's n choose 2, that's just going to be n times n minus 1 over 2. So using that same trick, we have 48 choose 2 as 48 times 47 over 2. So what is this? That's just going to be 26 times 51. That's going to be equal to 24 times 47. Now, if you were brave enough to do this, or the multiplication out and subtract it, and then try to get the final answer, you would be brave. I don't want to take a risk, right? I'm going to be like, okay, that's pretty risky to do. And then at the end of the day, the fraction is just equal to 51 over 26 times 51 minus 24 times 47. But those numbers are pretty big. So what I'm actually going to do is just take one easy and rewrite this 26. I'm going to rewrite it as 2 times 51 plus 24 times 51. I'll show you why I'm doing that in 1 second. But first I want to show that why it's clear that I can do this. Because if you have 2 of something and you add 24 of something, you have 26 of that same something, right? Also, let's play around with smaller numbers and think of it. Like if I have 7 times 3, no, that's a bad example. 7 times 6, I can split that up into a 7 times 3 plus a 7 times 3. So this is less of like a math team thing and more just like a quick way to add numbers. It's like tricks and stuff, especially on paper, because there'll be times where you have to do a lot of computation by hand and you want to like make sure that you do these tricks not only to save time, but also like to prevent yourself from just making a mistake. So the reason I did that is because you have 24 times 47 and you're subtracting it, right? So when you're subtracting these, you're kind of just doing 2 times 51 plus like 51 of something minus 47 of something is just that something times 4. All right, we're nearly done. This is a lot easier to do because it's just pretty simple, right? The first one is just 102. The second one is just 96. So 102 plus 96, that is 198. Now, we have 51 over 198 is our answer, right? But we can we simplify it? Yeah, because both numbers are divisible by 3, right? That's just the divisibility rule of 3 kicking in. But dividing to the top, we should have 17 as our numerator. And dividing 3 by the bottom, we should have 66 as our denominator, giving you the final answer of the final problem of this 7th grade competition as 17 over 66. So yeah, pretty fun problems.